Clinical science requires a great effort to collect data about different aspects of ataxia. The access to this data, however, is impaired by frequently uncomfortable storage, non-unified formats, codings, and wordings, and the communication gap between the clinical expert and the data analysts with their technical expertise. Here, we present a simple but intuitive approach to integrate information from different cohorts and to visualize them without effort. The first step is to merge the data from various cohorts into one database. To achieve this, some technical and semantical issues have to be addressed. Different naming of attributes. We know that date of birth, DOB, birth date mean the same, but the computer does not. Different coding, like storing male sex as M or as 1, and necessary transforms. For example, time information stored relatively or absolutely. We developed a data model in a simple tabular view to define these relations and programmed an import and mapping tool to apply these to all data available. In the end, we get a unified database as a basis for subsequent analysis. Visualization, sorting, and filtering can be done with numerous tools like Excel, but the matching of data based on patient identity and temporal proximity, sorting and selecting data based on definition criteria and plotting them in a comprehensive way is inconvenient, time-consuming, and requires some expertise with these tools. Therefore, we designed a web-based tool to perform the necessary data handling automatically and just ask the user what he wants to select and to plot. We provide plot areas and controls to specify the plot type, the attributes to depict, and additional criteria to sort and compare the data. Up to now, a handful of standard plots are available to visualize the integrated cohort data in order to generate or to graphically validate hypotheses about correlation between or temporal dynamics of different aspects of ataxia. In addition, a quick filtering via graphical definition of aspects or of quantitative constraints to reduce the data to define subcohorts for further comparisons is included. For maximal flexibility, we provide a workbench to calculate derived attributes and make them available for more complex visualizations. As a prototypic use case, we compared some attributes of SCA3 patients obtained in different international ataxia cohorts. For example, the distribution of the SARA score as a scale for severity of symptoms seems comparable when ignoring the controls in the ASME cohort. The visual approach does not replace a detailed statistical analysis, but gives a good first insight suggesting homogeneity between the different sources. However, integrating common statistical tests and fits to the plots to validate if apparent slight shifts are significant are desirable features in preparation already. The age of onset or the disease age at study entry as other exemplary characterizing attributes, however, are not provided in the dataset, but could be calculated using the workbench easily. Here again we find no obvious differences. Depicting SARA versus repeat length in a scatter plot or SARA versus the disease duration with a year of onset as reference yields comparable data for all cohorts. To address the disease progression, we used the attribute workbench to calculate the slope delta SARA divided by delta t for each patient and depicted it versus the repeat length. Obviously, none of these analyses or plots are novel. However, the integration of data, matching of data pairs, selection and normalization is not trivial and time-consuming when carried out manually. In contrast, it took only a few minutes with the visualization tool we present here.